Welcome to the last video of the Machine Learning from Scratch course presented by AssemblyAI. In this series, we implement popular machine learning algorithms using only built-in Python functions and NumPy. In this lesson, we learn about k-means. So first, we start with a short theory section and then we jump to the code. So let's get started. So k-means is an unsupervised learning method, which means we have unlabeled data that clusters a data set into k different clusters. Each sample is assigned to the cluster with the nearest mean, and then the means, also called centroids, and clusters are updated during an iterative optimization process. So this iterative optimization process is pretty easy. First, we initialize the cluster centers randomly, and then we do step 2 until they are converged, so until there is no more change. First, we update the cluster labels, and we do this by assigning the points to the nearest cluster center. And then in the next step, we update the cluster centers. So we set the center to the mean of each cluster, and then we do these 2 steps until there's no more change. So let's look at an example to make this more clear. First, we start with unlabeled data, and now let's say we want to find 3 clusters here. So we randomly initialize 3 centroids. So I hope you can see these 3 markers, so the black X. So these are the centroids, first randomly initialized, and now we assign the cluster labels to the nearest centroid. So here we have 3 clusters now, and now we update the cluster centers, so we calculate the mean of each cluster. So I think the blue center will be somewhere here, the orange one will be somewhere down here, and the green center will be somewhere here in the middle. So let's look at the next step. So yeah, here we have this. Here, for example, we have the green centroid. Then we again update the cluster labels. So we assign it to the nearest center. So I think this upper part here now will become orange because this orange centroid is the closest one. So let's look at the next step. So yeah, here we have it. Then again, we update the centroids. So again, we calculate the center of each cluster. For example, I think the green one will end up somewhere here, the orange one somewhere up here, and the blue one is already pretty good. So yeah, here we have it. Then again, we update the cluster labels. So now I think this upper part here will also become orange. Then again, we update the centroids, then again the labels, then again the centroids, and I think right now there is no more change. So now we can stop the algorithm and then we have it. And yeah, this is all that we have to do. I think this is pretty intuitive. And yeah, so right now there's no more change. So right now we are done. So all we have to do is these 2 steps. So first initialize this, and then we do these 2 steps repeatedly. And in order to find the nearest centroids, we have to know the Euclidean distance. So this is the formula, which is the square root over the sum and then the difference squared between 2 feature vectors. So this is all we have to do. So let's jump to the code. First, let's import NumPy as NP, and then let's create a class k-means. This gets an init function, and here as parameters, we give it k, so the number of clusters. Let's say by default this is 5. Then it also gets max iters, and let's say by default this is 100. And then we also give it plot steps if we want to plot the different steps of the clusters and centroids during the optimization. So now let's store this. So we say self.k equals k, self.maxIters equals maxIters, and self.plot steps equals plot steps. Then I also want to initialize empty clusters. So let's say self.clusters equals, and now we use list comprehension, and now we use an empty list for underscore in self in range self.k. So for each cluster, we put in an empty list here. And later here we want to store the sample indices. So let's say list of sample indices for each cluster. And then let's also initialize self centroids equals, and this is an empty list. And here we want to store the centers, and this is the mean vector for each cluster. So this is what we put in the init. Then let's define the predict function with self and x. And there is no fit method. We can do the prediction right away. And we also don't have y, because remember, this is an unsupervised learning technique with unlabeled data. So here we first, let's save self.x equals x. So we also have this in other helper functions. Then we also want to say self.n samples and self.n features equals x.shape. So here we assume this is already a NumPy ND array. Then we want to initialize the centroids. So first we choose a random sample from the, or k random samples from all the samples. So we say random sample indices equals, and for this we can use NumPy random choice of self.n samples, and then we want self.k, so k different choices, and we also want to say replace equals false, so we get different indices, and then we store this. So now we say self.centroids equals, and now this is a list. So here we say self.x of this random, of this index for index in random sample indices. So we do k different samples, and these are our initial centroids. And then we can do the optimization loop. So here we say, let's write a comment, optimize clusters, and now we say for underscore in range self.max iters. But of course we can stop earlier if there is no more change later. But these are the maximum iterations. And here first we want to assign the samples to the closest centroids, and with this we create the clusters. So let's say self.clusters equals self dot, and for this let's create a helper function, self.create clusters, and this should get self.centroids as the input. So down here, let's create this as a helper function, define, and then underscore create clusters, and this gets self and the centroids, and then for now we say pass. Then as next step, we want to calculate the new centroids from the clusters. So first we store the old centroids. So we say centroids old equals self.centroids. So we can compare this later if this is converged. And then we say self.centroids equals self.underscore get centroids. And now this gets self.clusters. So this is another helper function that we need down here. So we define underscore get centroids with self and the clusters. And now for now we say pass. So now once we have this, we check if self dot underscore is underscore converged, and now here this gets the centroids old and self dot centroids new. And if this is converged, then we break, so we can stop. And then again, we need this here as a helper function. So we define underscore is converged, and this gets self, then the centroids old and the centroids new. And then again, for now, we can say pass. And then I also want to have a helper function to plot the centroids and the clusters. So this only gets self, and for now we say this is pass. And then up here we check if we want to plot. So if self dot plot steps, we call self dot plot, and then we do this again after calculating the new centroids. If this is not converged and we go on, then let's again plot this. So then we are done with the optimization loop, and then down here we want to return the cluster labels. So for this we say classify the samples as the index of their clusters. And for this we say return self dot underscore get cluster labels, and now this gets self dot clusters as the input. And then again, this is a helper function that we put here. So define underscore get cluster labels with self and clusters. And for now we say pass. So now we are done with the predict method. So now we only have to implement all the helper functions. So again, here we first initialize this, then we update the clusters, and then we update the centroids by calculating the means. Then we check if it's converged, and if this is the case, we can stop. And in the end, we return the cluster labels. So for the cluster labels, we can say that each sample will get the label of the cluster it was assigned to. So in the beginning, we say labels equals NumPy empty, and it is of size self.n samples. And then we iterate for cluster index and each cluster in enumerate the clusters. And then we iterate over each cluster. So remember the clusters. So sorry, this is a typo, clusters. So this is a list. For each cluster, we have a list with the indices. So let's check if there are no other typos for clusters, but I think we should be fine. So now we have a list of the indices for each cluster. So here we say for sample index in cluster, and then we want to assign the cluster index to this label of the sample index. So we say labels of sample index equals the cluster index, and then we return the labels. So this is how we determine the cluster labels. So here we assign the samples to the closest centroids. So for this, we start with an empty list for each cluster. So we say clusters, and then we do the same that we do up here. So we say this is an empty list for each cluster. And then we can assign the indices. So we iterate for index and sample in enumerate, and then we enumerate over self.k. So this gives us both the index and the sample, not self.k, but self.x. And then we get the centroid index by saying this is self dot underscore closest centroid, and this gets the current sample and then the centroids, and then we add this to the clusters, so to this list. So we say clusters of the current centroid index dot append the current sample index. And then in the end, we return the clusters. So then again, we need this as a helper function. So we say define define closest centroid with self and then the sample and then the centroids. And here we want to determine the distance of the current sample to each centroid and then get the one with the closest distance. So we say distances equals, and then we use a list comprehension, and then again we use another helper function and call the Euclidean distance of, and here we put in the sample and then the point for point in centroids, so for all the center points. And then we need this as a helper function, but before we do this, let's get the minimum index, and we can do this by saying closest index equals numpy dot arc min of the distances, and then we return the closest index. So this is the closest centroid. So now we need to define the Euclidean distance function. So let's copy the name and then let's make this as a global function up here. So define Euclidean distance between 2 points or 2 feature vectors, x1 and x2. And we can do this in one line, return numpy. And now this is the square root over, and then here we have the numpy sum and the sum over, and then the difference x1 minus x2 to the power of 2. So this is how we calculate the Euclidean distance. So now we have this. So now we need get centroids. So in get centroids, we want to assign the mean value of the clusters to the centroids. So first we initialize the centroids. So we say centroids equals numpy zeros of shape self dot k and then self dot n features. And then we say for cluster index, and for each cluster enumerate clusters. So this is the input parameter. And then for each one, we calculate the cluster mean by saying this is numpy mean of self dot x of only this cluster. And then along axis equals 0. And then we say centroids of this cluster index equals the cluster mean. And then in the end, we return the centroids. So for each cluster, we calculate the mean of only this cluster and now assign this then to the centroid. So this is the get centroids. And then for is converged, we check the distances between old and new centroids for all centroids. And if this is 0, if there are no more distances, then we can return true. So first let's say distances equals, and then here again we can use the Euclidean distance, and then we can say centroid old of I, and then centroids new of I, and then for I in range self.k for each cluster. These are the distances, and then we can return if the sum over the distances, so this is a built-in Python function because this is a list, if this equals 0, and then we have no change and it is converged. So now the only missing function is the plot function, and I already prepared the code. You can also find this on GitHub. The link is in the description. So for this we say import matplotlib.pyplot as plt. And then down here we create a figure, and then for each cluster we scatter all the points in a different color. And then for all the centroid points we also scatter this point as a marker with the sign X in the color black. And this is all we need for our k-means class, so now we can test the code. And for the testing, I also already prepared this and will simply copy paste this. But before we run this, I noticed 2 errors. So first, in NumPy zeros, the shape has to be an inner tuple. And then up here, I also made a typo for cluster index and cluster in enumerate clusters in get cluster labels. And now this should work, hopefully. So I want to do one more thing. I want to say NumPy random seed and set this to, for example, 42 to make this reproducible. And then we create blobs with make blobs from Scikit-learn datasets. So here we specify 3 centers. Then we get the number of different clusters by getting the unique labels of y and getting the length. And then we create our k-means instance with k clusters. And then we say max iters and plot steps equals true. Then we call k.predict, and in the end we plot this again. So since plot steps equals true, this should now plot all the different steps. So let's save this and run this. And first here we have the initial centroids. And now in the next step, it should update the centroids. Yeah, then it should update the cluster labels. Yeah, then again, it should update the centroids. Then again, the cluster labels. Then again, the centroids, the cluster labels, the centroids, the cluster labels, the centroids, the cluster labels, the centroids, the cluster labels. And now there is no more change. So now we are done. And this works. So now we implemented the k-means from scratch using only NumPy and built in Python. So yeah, I really hope you enjoyed this lesson and also the whole course. If you didn't watch the other videos, then you can find the links to the videos or to the playlist in the description below. Also, as I said, the code is on GitHub, so please check that out as well. And then I hope to see you in another video on the AssemblyAI channel. Bye.